previous years. Before we get into the movement of particles, we're going to look at different states of matter. So we have 4 states of matter that we know of: plasma, gas, liquid, and solid. We know that plasma is like a gas. It's just a gas that is more excited, so it has become ionized. It lost some of its electrons, but I mean, I'm not going to explain it again, but you know, this has everything to do with the quantum theory, whereby the electrons leave and come back. So at this point, the gas is ionized. We call it plasma, but it is really just a gas. So here we have the different changes of states. So if we go from, for example, gas to liquid, we call it condensation. The reverse is called evaporation, when liquid becomes a gas. A gas becoming a solid, here they call it deposition. You probably learned sublimation. Very often we use the same term both ways. So from solid directly to gas, we call it sublimation, but we use the same term for both very often. For liquids, liquids that are becoming solid, they're freezing. And if they're going from solid to liquid, they are melting. So this is just a little review, things you already know. Moving on to the particle model. So as in atoms, right? Matter is composed of particles that are very small, we know that, and there's space between them. This comes from last year's theory that we covered from Democritus. Particles attract or repel each other, and this force varies according to distance. This makes sense. Particles in a solid are very close together, so they have more interactions than particles in a liquid or particles in a gas that have very little interaction, whether it's attraction or repulsion, because they just don't interact. There's so much space between them, they don't really encounter each other that much. And particles are always in movement. Now, what kind of movements do we see in matter? There are 3 types. So we have vibration. There's 3 types of vibration. Your molecule can bend back and forth like this, or could stretch, either symmetrically, so both ends are stretching to the same extent or pulling to the same extent, or asymmetrically, so one side is pulling more than the other side. So these are types of vibration within matter. Then we have rotation. So your molecule may turn on itself in one direction or in the other. And for translation, well, it's just moving from point A to point B in a straight line. So in solids, we have only vibration. So you'll have, again, the bending and the stretching. And that's why your solids are very stiff, right? There's a structure, the particles are arranged in a certain way, and they can't move much. They're really compact together, they're really close together. And because they're so close, they cannot be compressed, so they are incompressible. And that's also because, well, that is actually because of the forces between the particles, right? If you put 2 atoms very, very close together, their electrons will tend to repel each other. The same way their nuclei, because of their positive charge, will also tend to repel each other to some extent. So we can put them close together to make a solid, but to a certain degree. Then we have liquids. So in liquids, we have vibration and rotation mainly. There's also some translation, but very little. That's why I put it here in smaller font, because there is some, but not much. Those particles are well, they're a little further apart, which allows them to move a little bit more. That's why when you pour a liquid in a container, the liquid will tend to take the container's shape. There's more flexibility there as far as the shape goes. They're still incompressible. The particles are still fairly close together. So again, the particles are repelling, so we can't really compress them that much. And a gas. We know that gas particles are really, really far apart. So we can actually compress gases. So here it says they're compressible. There's 3 types of movement: vibration, rotation, and translation in a gas. So it has all 3. And because of this translation, the gas particles move in all directions, and they'll tend to use the whole space available. So they'll fill out their container. That's why if you spray something in one area, like perfume, through the phenomenon of diffusion, that gas will tend to travel in order to fill out the whole room in which you sprayed it. It's going to move, yes, from area of high concentration to area of low concentration, but in the end result will be that it covers all the space available, and that's because of the translation type of movement. So the particles move in different directions in straight line. Okay, and then I told you that it's compressible because the particles are really, really far apart. Now, if we look at the energy that those particles have, we can quantify that in terms of disorder, also called entropy, which is represented by a capital S. The warmer a substance is, the more the particles are going to move, right? They're going to vibrate more, they're going to rotate more, they're going to translate more. So that means they're going to be very excited and there's going to be more disorder, or as it says here, more entropy. So if we were to put our different states in order of entropy from very organized to very disorganized, or low entropy to high entropy, we have solid first, very little disorder, the particles are organized, gases, and at the far end we have plasma where there's a lot of disorder, the particles are very excited, there is a lot of entropy. So to summarize, we have a little table here, a chart. So if we look at shapes, particles, solid particles, because they're very structured, they're assembled in a certain lattice, right? The shape is fixed. In a liquid, the particles are looser, so there's more flexibility there, as I said before, so the shape is not defined. In a gas, the particles are so far apart, definitely the shape is not defined. They can take the size, or the shape, I should say, of their container. As far as volume goes, again, because of the lattice, the solid has a definite volume, it can be measured. The liquid has a definite volume, we can also measure that. It'll take a certain amount of space, even if that space can change shape, the space is definite. For gas, it fills up the whole container, so the amount, not the amount, but the volume may change, it's not definite. Ability to flow, or ability to flow, solid cannot flow. A liquid, yes, it can flow. A gas as well. Can be compressed. It's only the gas that can be compressed. And can the volume change with heating? For a solid, you can change it a little bit. The liquid as well will, if you heat up a liquid, will take a touch more space. A gas will be much more affected by a change of temperature. Okay, now when it comes to kinetic energy versus temperature, so a temperature is really a measurement of the amount of movement in a substance. So the temperature is the macroscopic item, so what we can see, what we can measure and see to the naked eye, versus the movement itself. We can't see it. We need a microscope, right, to see the movement of particles. So that's why we call it, obviously, microscopic. So temperature is a macroscopic measurement of a microscopic reality, which is the movement of particles. So in a gas, if you increase the temperature, that means you're going to have more energy, right? And the particles are going to move faster, thus the word velocity. The way we calculate this is using this equation here. So kinetic energy is equal to half the mass of the substance times its velocity or speed squared. We saw that last year, so you already know how to work with this equation. It's the same as what we covered in the physics section. So in a gas sample, do all particles have exactly the same speed? The answer is no, right? Our particles are going to be at a certain temperature, but that's really an average temperature. So most particles will have that given temperature, but a few will be colder, a few will be warmer, therefore they'll have more or less the same energy, but there can be slight variations. That is because, in part, because of the collision. So when I have two particles, just think of two balls, let's say, that roll towards each other. Well, when they hit each other, not only will one of them or both of them change trajectory, but one of them may slow down and the other one may accelerate depending on the force that was given or that was put in throwing those two balls. It's the same thing with the particles. When they collide, they exchange energy, and one of them may accelerate, another one may decelerate, and because of that amount of energy and because of that change of speed, well, this here will change, right? And we said that this here is a measurement of temperature. So if a particle gets more energy out of that collision, this will increase, and the speed will increase as well. While the other particle will slow down, which translates into a decrease of energy and a decrease of what we see or what we measure as temperature. Okay, so this here, microscopic, sorry. So this we can see only with a microscope, which is the movement of the particles, but we can measure that in terms of temperature. Okay, so here we have different graphs that show you the relationship between the amount of energy that that different particles have, and actually, let me rephrase that. The amount of energy that each particle within a group has. So the way this is distributed here, so you have the particle velocity. So here we have higher speeds, here we have lower speeds. So if we are to look at this curve here, what it really says is that, for example, let me just, okay, I have a pen. Let me just take and use a pen. Okay, let's say this. Okay, so let's say here I have 5 meter per second. Well, at 5 meter per second, I might have, I don't know, 10 particles that are going at 5 meter per second. Then at 10 meter per second, I might have, so about here, I might have, I don't know, 20 particles that are going at 10 meter per second. So that's the way you read this. So if you look at the curve, for the very small values of speed, I have a lower amount of particles. For the average speeds, I have higher amounts of particles. So most of my particles have average speeds. Very little particles have very high speeds. So as I was describing before, not all particles have the same amount of energy and therefore the same amount of speed. So my average amount of particles in that group, the average amount of particles, have average amounts of speed. Now here, depending on the temperature of the medium, of the environment, the particle's velocity will change. So in blue I have lower temperatures, so a colder environment. So most of my speeds are in the lower section, right? Now for the green curve, average temperature, well, my speed, you can see it's going towards this side. So that means my speeds are increasing a little bit. If you look at the red curve, well, again, it's moving even more in the direction of the higher values, which means that if I increase the temperature of the environment, well, in that case, my particles will gain velocity. They'll gain kinetic energy and therefore velocity, or vice versa, because they're dependent. Here I have number of particles versus kinetic energy. It's the same story. Kinetic energy, is basically the same as velocity because they are interdependent because of that equation, right? Kinetic energy is equal to half of the mass times the velocity squared. So if the velocity, the speed changes, the kinetic energy will change and vice versa. That is why this graph as well as this graph are very similar. Now, another way to look at it, if I just lower the page a little bit, sorry about that. Okay, if you prefer this type of graph, then in green we have a regular, let's say, temperature, or my initial temperature. So most of my particles, as you can see, have not much kinetic energy, right? They have maybe 5 kilojoules of kinetic energy. The rest has 10, 15, or 20, and you can see that as we're moving towards the higher values of kinetic energy, less particles have that amount of energy. Now, if we were to heat up this group of particles, you can see that this here is increasing versus what we had before. So we have more particles that have 10 kilojoules than before. We have more particles that have 15 kilojoules than before, more particles that have 20 kilojoules than before. Sorry about that. My dog doesn't like my lessons, seemingly. Okay, so here, and you can see that the particles that have 5 kilojoules, well, that went down here, right? Because all the particles seem to gain more energy, so the whole graph is basically shifting to the right towards the greater values of kinetic energy. Finally, we have the last slide here. So the kinetic theory of gases, all this to say, or not all this to say, but one more thing I have to add, is that to be able to compare things together, gases together, we need some kind of reference, some kind of some kind of reference to work with. So we're going to pretend there is an ideal gas. So now let's analyze how that ideal gas would behave, and we'll keep comparing to that ideal gas. So first of all, a gas is still made of particles, whether it's ideal or not, still made of particles that are very small. Their size is negligible compared to the containers, so it'll still occupy the whole space available as well. The particles are still in motion, and when they travel in a straight line. Now, where it's a little bit different is that the particles in this case, for a perfect gas or an ideal gas, will not interact with each other. So they're not going to be some side interaction that's going to mess up the whole, result thing. So they don't have any attraction, they don't have any repulsion. Their reaction is unrelated to other particles. So we'll be able to study them individually and then compare to real gases to see how the results converge or diverge. And the particle's energy is proportional to their temperature. We saw that already. That already makes sense. So the point that really changes, or that it is really different for an ideal gas, is this one here. So the particles do not interact with each other, as opposed to with a real gas. Of course, there would be some kind of attraction or repulsion that would, kind of interfere with some of their properties. So that's it for that. So this is the end of 2.1. Stay tuned for your next episode.